Next, let us discuss the concept of compound interest. If you recall, the compound interest is paid at every interest due time by taking the principal plus the interest paid as the net principal. Let the investment period 0 to t be partitioned as t naught, which is 0, t1, t2, and so on till tn, which is equal to capital T. The interest rate be given by R and the principal be denoted by P naught. At T is equal to T1, we have just like simple interest, P of T1 is equal to P of 0 into 1 plus RT by N. This is the interest per period, and at the first interest due time, your interest is paid like this because you have not accumulated any interest so far. Therefore, it is just like the simple interest. And now you consider this as the principal for the period T1 to T2. And therefore, at T equal to T2, the total amount that you accumulate is now, instead of P naught, we have P of T1, that is this amount. For this, we will be paying the interest. Therefore, it will be 1 plus R into T divided by N. That is, keeping this as the principal, you calculate the interest just like how you calculate for simple interest. So now for PT1, we can put this expression to get P of 0 into 1 plus RT by N square, because 1 comes from here and already you have 1, so both together square. So continuing in this way, we can obtain the formula for the nominal value, that is the maturity amount. P of capital T is equal to P naught into 1 plus RT to the power of N, because at every step you accumulate one factor, and therefore at the nth step you have to the power of N. So that is the formula for compound interest. Let us see an example. Let's take the same example that we have considered for simple interest, where Meg invested 100 rupees in a bank fixed deposit scheme at the rate of 10% per annum and for the period of 2.5 years. And the payout of the interest is quarterly, and therefore now we can use the compound interest formula to obtain the maturity amount, that is the nominal value of the fixed deposit, if the interest is calculated at the compound interest basis. As we have done in the last case, it is N is 10 because you have 2.5 years and quarterly basis you are paying, and therefore there are N times the interest has to be paid. The final time is 2.5 years. The initial principal amount is P of 0, which is 100, and the interest rate is given by R equal to 0.1, right? So P of T is given by, you just apply, put all these values into the formula. We get 100, that is P naught, into 1 plus 0.1, that is R, into 2.5, that is capital T, divided by 10, that is N, to the power of 10. And that is approximately equal to 128. Therefore, the interest, net interest obtained in compound interest basis is 28. If you recall, in simple interest for the same parameters, the interest was given by 25 rupees. Therefore, we obviously have a little higher interest here because it was done as a compound basis. What is the cash flow? The cash flow is initially paid 100 rupees to the bank. Therefore, makes cash flow at the beginning is minus 100, and then he never obtained any interest because the interest was kept with the bank and the bank was compounding it. Therefore, he was not paid any interest. Each interest due date, in his hand nothing was given. Therefore, everything is zero. And at the maturity, he was given the nominal value, that is the maturity amount, which is 128. So that is the cash flow in this case. Now, instead of paying every quarter, if the bank pays every month, okay, then what happens? You can see that in 2.5 years, then the bank will pay 30 times the interest, right? So therefore, the interest per period is now 0.1 into 2.5 divided by, now it is 30, okay, and then to the power of 30. That will lead to little higher maturity amount, that is 128.27, obviously, because you are now paying 30 times. So this shows that as the frequency increases in the compound interest scheme, the maturity amount also increases. That is what we can clearly see from this formula. The interest paid in this case is 28.27. If you recall, in quarterly basis, we had 28 rupees. Okay, so it's slightly higher than the quarterly compounding scheme. Next, let us introduce a important concept called effective interest rate. In the case of compound interest, in the examples that we have discussed, we saw that although our interest rate was given as R is equal to 0.1, that is 10% per annum, and for a period of 2.5 years, the final interest that we obtained was, in the compound interest, we had 28 quarterly, right? In the monthly, we had 28.27. Let's take the first two example. We had 28. Okay, so here you can see that although our interest rate was 10%, but finally the net interest that we obtained was 28. That is due to the compounding nature of the scheme. So if you see effectively, what was the interest that we obtained here is actually 11.2%, right? In this example, although your interest that was quoted was 10%, because of compounding, we got slightly more. We would have got 25 rupees, but we got 28 rupees. That amounts to 11.2. That is, if we represent it as RE, it is 0.112 is actually the interest rate that we obtained due to compounding. This is called effective interest rate. This basic interest rate, which in our example is 10%, is generally called the nominal interest rate or simply interest rate. We often will not refer it as nominal interest rate. We often refer it as interest rate. But if you want to refer this effective interest rate, we always say effective interest rate. So given all the relevant parameters, how to calculate the effective interest rate? If you see, let R be the total return obtained at t equal to t. That is, in our example, it was 28, right? Because 100 rupees we gave and we got 128. Therefore, the return was 28. okay, per annum, then R can be written as P of t minus P of 0 divided by t, right? So you can see that you have given P of 0 as your capital, that is the principal initial amount, and you got back P of 0 plus R, right? So the return is therefore R. What you got is the profit you got out of this is R. Okay. So from here you can obtain the this relative interest formula. So RE, therefore you can derive it to be, what is this? This is nothing but R by P of 0. Now you substitute R here, you have P of t minus P of 0 divided by t into P of 0. Now you know from the compound interest formula, you know how to write this. So you can use the compound interest formula here, and then you can get the final formula for the effective interest rate. Let me leave it as an exercise to you to complete it. The compound interest we have discussed so far has discrete payout time. That is to say that the frequency is finite. One can imagine the frequency, that is n, to tend to infinity. Okay, this is often used in theoretical situations, and in such case the compound interest scheme is called a continuous compound scheme. If you recall, in the compound scheme the formula was P of t is equal to P naught P of 0 into 1 plus interest rate per period to the power of n, right? Now we'll take n tending to infinity on both sides, and note that the exponential function ex can be written as limit n tends to infinity 1 plus x by n to the power of n for any real number n. So keeping that in mind, you take limit n tends to infinity here, we get this side there is no n, therefore there is no limit. You have so in fact you can bring this also out. You have limit n tends to infinity 1 plus rt divided by n to the power of n. So you take this quantity as x and look at this formula, you can see that this is nothing but P naught into e to the power of RT, right? So that is the formula for the continuous compounding interest. We summarize the different types of interest rates that we discussed so far. The first type is the simple interest. The formula is given by this. We see that the maturity amount, that is the nominal value, is given by the principal amount into this factor. This is called the growth factor. We can see that in simple interest, the growth factor is linear. That is, in simple interest, we have a linear growth. Next, we have seen compound interest. There are two types of compound interest we have discussed depending on whether the frequency n is finite or it tends to infinity. In the first case, that is when n is finite, we have derived the compound interest formula. To distinguish it from the case when n tending to infinity, we may sometimes call it as discrete compound interest. The formula is given by this. The maturity amount P of t is equal to the principal P naught into the growth factor. You can see that in the case of discrete compound interest with frequency n, that is finite, the growth factor is geometric, that is the growth is geometric. In the other case, that is in the continuous case, when n tending to infinity, we have the nominal value equal to P of 0 into e to the power of RT. Okay, so in this case, we have an exponential growth with the growth factor being e to the power of RT. We note that in all these cases, we have taken the interest rate R to be a constant. Next, let us consider the case when the interest rate R is a function of t. In this case, we can obtain a model which involves a ordinary differential equation or a integral equation. Let us derive this model. For a given number delta t greater than 0, we can see that the net interest obtained in the interval t comma t plus delta t for any t in the interval 0 to capital T is given by P of t plus delta t minus P of t. So that is the interest that we obtained during this period. Assuming that delta t is very small, we can approximately take the compound interest in the interval t comma t plus delta t as a simple interest. Therefore, we can write P of t plus delta t minus P of t, which is the interest obtained in this period, is approximately equal to the simple interest rate you can give, which is given by this. Okay, so starting from the time t at which your principal was P of t, you obtain the simple interest at the time t plus delta t, that is at this time, that is given by this. Although we have compound interest, since our delta t is very small, we may approximate that compound interest by this simple interest. Now dividing both sides by delta t and then taking the limit as delta t tending to 0, we can get limit delta t tending to 0 P of t plus delta t minus P of t divided by delta t is equal to R of t into P of t. So I will not put approximately equal to here, because as you go on decreasing the value of delta t, the compound interest value will go more and more close to the simple interest value, and therefore in the limiting case, in fact, we can write equal to instead of approximately equal to. So this leads to our required ODE model given by dp by dt is equal to R times P, that is this one. Okay, R is a function of t. Now you note that if you assume R to be constant, then you can directly integrate this and get our continuous compound formula, which we obtained in the previous case when R is constant. That is, you can write this as dp by P is equal to R into dt. If R is a constant, so if you recall from your ODE, it is just a separation of variable. You have log P is equal to r times t plus log some constant you can take, and that implies P by C is equal to e to the power of RT. That implies P of T equal to C times e power RT. But at T equal to 0, we have P equal to P of 0. Therefore, we have P of T equal to P of 0 into e power RT. Now put T is equal to capital T, we get P of T is equal to P0 into e power RT. This is what we obtained as the formula for continuous compounding. Okay, so that can be obtained from our model, ODE model also, in a particular case when R is a constant. But this model holds even for R non-constant, that is a function of t. Now let's take this ODE and take the integration over the interval 0 to t. So dp is equal to r of t, p of t, dt you can write, and then you take the integration over this, you get p of t is equal to p of 0 plus integral 0 to t r of s p of s ds. Okay, so which is also a model, which is basically a integral equation. This is also our required model. We can see that if r and p both are continuous, let's call this as 2 and call this as 1. If both are continuous, then 1 and 2 are equivalent. How will you see this? You can see this using fundamental theorem of calculus. Okay, but the model 2 has an advantage that it can be used even when R and P are not continuous functions. Okay, even as long as they are integrable functions, this equation makes sense. Note that 2 can be used as long as R and P are integrable. Why? Because you have to make sense of this integral, right? So that is the main problem. If R and P are integrable, then this term makes sense, and therefore we can obtain P of T. Okay, whereas in this case, you can see that R into P should be continuous in order to make this integral, this differential equation meaningful, right? So in that way, 2 is more general. So often in studies, people use this integral form rather than the ODE. So this completes our discussion on interest rates. Next topic is present values. What is mean by present value? So far, what we have done is for a given principal, that is the initial payment P naught, we have derived a model for the maturity value, that is P of T. Of course, we are also given the interest rate, terminal time T, and the frequency N. Then we found the nominal value P of T. Now, what is our interest in present value is, given the maturity value, we have to find the present value, that is today what we may have to invest in order to get the future value given by this amount. That is the idea of present value. So suppose I want this much money after say 2 years, given the interest rate and the frequency and so on, how much do I have to invest today? That is the question posed to us, and present value is to find a formula to get the amount that we need to invest in order to get this after given time. So in one step payments, it is not very difficult, because if you go recall in simple interest case, P of t is given by this formula. So from here we can directly obtain P of 0 as P of 0 is equal to P of t into 1 by 1 plus r times t, right? So you can immediately find this. Similarly, in the case of compound interest, if you recall, the formula is given by this. From here, we can again find the present value P of 0 is equal to P of t into 1 by 1 plus RT by n the whole power n, right? So this is the formula for present value. And if you go to continuous compound interest, if you recall, this is, we simply call this as compound interest when n is finite. Actually, it is also called discrete compound interest. Okay, in continuous case, we have P of 0 is equal to P of t into e to the power of minus r t. The procedure of finding the present value for a future amount is referred generally as discounting. Okay, so you want P of t. Okay, this is surely the money which is more than what you have to invest. Given there is no risk, you invest today is actually less than what you are going to get at the maturity time. Therefore, given this, obtaining this is called discounting. Correspondingly, the present value is often referred as discount value. The procedure of doing this is called discounting, and the present value is often called discount value. And the factors, so if you recall, in each case, we had a factor multiplied with P of t in order to obtain P of 0. These are called discount factors. Okay. In the case of simple interest, it was, the discount factor was 1 by 1 plus r into t. In the case of compound interest, that is discrete compound interest, it is given by 1 plus RT by n to the power of minus n. And in the case of continuous compounding, it is e to the power of minus RT. See here, the present value, since we had just one step from P of 0 to P of t, we had only one payment at the initial time, and then there were several cases where the borrower will pay you interest, and finally the final settlement comes. Okay, in this case, you saw that the present value is very easily obtained, a direct consequence of the formulas that we have obtained so far. The complication is when you have in between, if you also make some payments. Okay, Then the formula is little bit involved. The concept of discounting plays an important role in pricing options because it provides a measure of the risk-free future value of money. Therefore, we have to carefully understand the meaning of present value. Here it is very clear, but in more complicated cases, we have to understand it more carefully, which we will do in the next class.